Dr. Sasha Eichstrasch, head of the department. He will talk to us on metrology for digital transformation. May I request you, Doctor, to make your presentation. Thank you.
Thank you very much for the invitation and the possibility and opportunity to tell you about some of the aspects of digital transformation and the role of metrology. Before I start, there is an echo. I can hear myself with a delay. Maybe somebody can mute microphone. Of course, in this presentation, I can only touch on some of the aspects of digital transformation in metrology and the role of metrology in digital transformation. So bear with me that there may be some aspects that you may have expected that are not included in this talk. If you're interested, then feel free to contact me afterwards via email or otherwise, and we'll then find a way to have a conversation or extend the discussion. This year, several, if not all, of the major international bodies and institutions of the scientific and quality infrastructure have signed a joint statement of intent stating their willingness to collaborate towards a digital transformation in the scientific and quality infrastructure. They are starting and focusing on the development, implementation, and promotion of an SI digital framework, which originates from earlier work from CIPM and BIPM. This statement is important because it marks the starting point for a year-long collaboration, cooperation, and joint work for the next decade, at least, I would say. All of these organizations have, of course, started their own individual endeavor in digital transformation. And with this statement, they're now going to bring the different developments together and collaborate towards an interoperable digital quality and scientific infrastructure worldwide. Of course, also CIPM and BIPM started much earlier on this. Last year in February, there was a huge international online conference organized by CIPM and BIPM called the International System of Units and Fair Digital Data. And when you look at the topics from that conference, you see many of the aspects that are relevant for all institutions in the quality infrastructure. It starts with the representations of course, in metrology, the units of measurement. It's further to the services that we provide and their digital transformation and the interoperability of such services among us and our customers, but also across the quality infrastructure. Machine actionable metadata and data and fairness of data are requirements to achieve such interoperability. And later in my talk, I will say a few words more about what that means and how we can approach it. And an important aspect, in particular for the metrology community, is the digital transformation of the services that we provide. For instance, by transforming our certificates to a digital calibration certificate, digital certificates of conformity assessment, digital testing certificates, and so on. And I will also say a few words on what that means at the first step, and then further going towards the coming years and increasing the digital aspects of it. And also a new area, the readiness of data for artificial intelligence and machine learning. I will not go too much into detail on this one here, just to tell you that it's also, of course, a major topic in metrology institutes because it requires new competences. It enlarges the area of our services. So in the future, for instance, metrology institutes will also provide reference data sets, not only reference materials, to assess artificial intelligence methods. They will provide metrics to measure the quality of artificial intelligence and much more. But there, we're just at the beginning, and there's a lot of research to be done before that. We can identify many of the challenges that are that we are facing in the digital transformation metrology by looking at sensor networks. Sensor networks or systems of systems is something that we see in an increasingly amount of applications in smart grid, electricity, gas, water, and so on, smart city, smart factory, even in automated vehicles, being it on land or in the water. In all these applications, we see an increasing amount of digital sensors, down to small MEMS-based sensors that provide new challenges for us metrologists when it comes to calibration and traceability, but also new possibilities and opportunities for us, like integrating metrology directly into the communication and computation capacities of such sensors to achieve something that we may call smart traceability, meaning a sensor not only providing its measured values, but also the unit of measurement and measurement uncertainty may be together with a digital calibration certificate. What makes different is also that these sensors are used in an interconnection. So it's no longer the individual measurement instrument, the individual measurand at one place that is important, but the combination of several of such sensors, being it a homogeneous sensor network, like in a gas network, the measurement of pressure at different points in the network, or being it the temperature measurement in a room using a localized temperature sensor network. But there are also heterogeneous sensor networks, like for instance in a factory, where you use different modalities to assess the remaining lifetime of an infrastructure that you need for the production. And there you may have a microphone, a voltmeter, vibration measurement, temperature, and many more. And from the combination of these, for instance, using methods of machine learning, you want to then derive the quantity of interest, the measurement of interest. And that brings us again to the measurement uncertainty question, the traceability question from the point of view of mathematics and statistics. How do we propagate uncertainties from the individual sensors through all the steps in the network? How do we incorporate the effects that originate from the networking issues like timing and synchronization? How do we provide really applicable in practice applicable methods for the evaluation of measure uncertainty for machine learning and artificial intelligence? The data sets may be huge, may be volatile, may be of different structure or even unstructured. So big data. How do we provide measurement uncertainty for this? You see many challenges ahead of us as metrology institutes and laboratories. Even when you look at the individual sensors, we see an increasing complexity. Of course, that's nothing new. We as metrologists are used to instruments becoming more complex in their evolution and their development. But we see a kind of disruption here in the last couple of years because of the increasing integration of digital technologies into the sensors. So you have more and more a combination of the actual physical measuring elements and some digital elements, the software. And the software may try to compensate for unwanted effects. It may combine several measuring elements that are inside of the instrument to derive a measured value. Or it may do even more like that, like an internal calibration based on some reference that is already integrated into the box. This is challenging for metrology, of course, because at the first hand, we don't have access anymore necessarily to the actual measured values, only to the pre-processed values. Does that mean that our calibration standards are still working for this? We don't know yet, or at least I haven't heard of anyone who knows that for sure. Instead, we saw already a couple of years ago that in some areas where companies try to integrate software compensating for unwanted effects, that these sensors then show very strange results in certain calibration scenarios. Nonlinear jumps in their value, strange decrease of values, and so on, just because the software was trying to compensate for something that wasn't even there yet, but the sensor was used in a situation that wasn't foreseen by the manufacturer and the software development. When we have such a black box in our calibration labs, how do we provide a reliable calibration? How do we ensure traceability for such sensors? I think there are huge challenges ahead of us. Not talking about something that is at risk here as well, and that is the maybe wanted or maybe unwanted manipulation using intelligent software that identifies when there is a calibration. Just saying. One example that we already saw at PTB that even goes much further beyond this before mentioned combination of software and hardware is the combination of digital twins and hardware measurement. This is an example from optics, from optical metrology. This is a measuring instrument you can buy on the market. So it's already there, it already exists. It's not a research anymore. And this is using a complex arrangement of lenses and rays to measure the surface of an sphere. And what's happening here is that you have the physical measurement creating these interference patterns you see here on the left-hand side. And then you have a simulation, you have a digital twin of the whole infrastructure with all the lenses, the physics of the lighting and so on. And you have a model of the surface under test. And then in a simulation, you adjust the model of the surface under test of your measure arm, so to say, until the simulated pattern looks as close as possible as the measured pattern. And only this combination of physical and simulated measurement gives you the measurement result. How do you calibrate such a thing? How reliable is it? What is the quality of this? Many questions that need answers when we want to have metrology for these kind of instruments available. Of course, metrology institutes are only one, an important but only one element in the quality infrastructure, in the assessment and assurance for trustworthiness of products and services. It starts with the development of a product, then you have the conformity assessment, the manufacturing, the product is distributed on the market, it's in operation, and then at some point in its life cycle, it is recycled. Now, with digital transformation, we see more and more examples where this physical life cycle is accompanied by a data life cycle. So you have data that is created in the design and development process, the data from the conformity assessment, the data that is gathered in the field during the distribution and operation of it, and that then may later also be used for the recycling. Of course, there are many bodies, institutes, companies, and places where this digital information can be enriched. Right now, it is distributed across various bodies and data places. In the future, though, this information may be gathered together, summarized into what we call a digital product path. Because this gives us a lot of benefits. We can learn from the data during distribution operation, also for the conformity assessment. The company can also learn for its future design. And then in the recycling, we can learn from the data during distribution operation to improve the effectiveness of the recycling. We already see early developments in these directions, like in the standardization communities, the work on smart standards and certificates in metrology and conformity assessment. The increasing use of cloud platforms to bring together different data sources. The use and integration of artificial intelligence and early steps towards a digital product path. Again, many different institutions and bodies and areas come together here. We have the regulatory framework, the standardization, and then the metrology, accreditation, and calibration interplay for the non-legal metrology part. We already see developments like digital certificates for calibration and testing, the early steps in end-to-end digital processes with the aim to make the quality infrastructure more efficient, but also with the need to have harmonized interfaces and data. And the needs here become even more clear when you look at the legal metrology part of it. Here you have the conformity assessment and market surveillance that also need to be taken into account. And of course, this needs to be interoperable with the developments in accreditation and calibration for the non-legal metrology part. So we need to work together in order to have an interoperability of the developments. And to start this interoperability, let's have a look at what is going on in the standardization community. Just recently, there was published a white paper on scenarios for digitizing standardization and standards. And in that white paper, they have presented these 5 levels of digital maturity. It starts with level 1, where you have a digital document, so the standard as a PDF document, for instance. Level 2, you have a machine-readable document, so you have some structure in the document that can be used by a software to extract certain information, certain paragraphs from a search, like give me all the definitions or extract the requirements and so on. Level 3 is then going even further by having machine readable and executable content. So you have the information that is contained in the standard provided in such a way that the machine can extract the information, not only the text paragraph. And machine interpretable content mean that the machine can also work with the information itself. Then the white paper adds a level 5 to that is looking far in the future, and that is machine controllable content, saying that a software may be able to adjust a standard or compile a standardization document. Of course, there are many things that are required to achieve this level 5, and it's clear that this is something we will not see in the next 5 or 10 years, but maybe in 15 or 20 years, first steps in this direction may be seen. We need machine-readable semantics, so ways to provide information about the wording and taxonomy in the document for a machine. We need interfaces to applications and platforms that can be used by a software. We need models of the data that we use, so the structure of the data in such a way that it is interoperable between different domains and areas. And then we can have machines adapting and creating certificates and standards. There are, of course, some consequences. First consequence is that you may no longer need documents because a software doesn't need a document. Software only needs the information. And also we as users only need the information. Is this product that we have in conformance to standards and regulation? Is the calibration of the measuring instrument still valid? Is the instrument working according to a given standard, and so on? But it also means that we need rules for the software processes and the accreditation. When we have software, so machines adapting and creating certificates and standards, and we will see more and more automated processes in the quality infrastructure. Not talking about the internal, like in a lab, automated processes, but between different bodies, like an automated process for conformity assessment to prepare the final decision to be made by a user. To give you a more illustrative example of what that means, here you see a display, kind of a dashboard that you very likely have seen before in this or other ways on an airport. It provides you exactly with the information you need with a high level of confidence. You don't need to know why your flight was cancelled or is delayed. It may be of interest and you may be curious why it's so, but you don't need that information. You only need to know, will my flight be delayed? Will it be cancelled? Because then you have to take some action. And you need to have a high level of confidence in that information. Because if it's wrong and your flight is not cancelled and you take some action, then you're losing money and time and of course you're angry. So this is an example of extracting the information that you need at a certain time without needing to have a document or the whole set of information at your fingertips. Of course, we start where we are now, and this is in most areas, it's level 1. So we have a digital document. We may provide the certificates as a PDF document. Standardization communities are already providing standards as PDF document for download. But how do we create those? This process can also and also needs to be digitized. That means, first of all, that we from the placement of the order to the provision of certificate have a working digital process internally, that we can use electronic signatures and seals not only internally or nationally, but accepted internationally, which is not that easy. And we then provide the certificates and reports at least via email, so digital, ideally over some customer platform or service provider. Already this step can be challenging when you want to do it right. Doing it right means that you don't have different islands of digital solutions in your process internally, but that the data that comes from the placement of the order from the customer is used in your internal document management system together with all the metadata. That this metadata is automatically provided to the laboratory, to the place in your institute that is doing the actual examination, like calibration or conformity assessment, that this information can then be enriched and provided and put into the certificate, and then an invoice is created and the certificate is provided. So the information is handed over from one step to the next without a human needing to manually type something in from copy and pasting it from one platform to another. To do this right is already a challenge, depending on how well prepared you are with your processes. From this, we can then go to level 2. That means we have to break up the PDF document and have to use something that provides us with some structure that can be searched for. Like you may have, as in an XML document, you may have certain structure elements saying, here's a measurement result. And then you may have in that measurement result certain substructures, like in a hierarchy, that you can again search there. So you can then write a software that extracts the information. Of course, it's still a manual workload because you as a human have to look into the structure of such documents beforehand, and you have to very carefully prepare the software and so on. You can, however, specify the type of information easily in such a structure, and you can then have the software parse the document to extract the structure. Like for instance, you can have a software parsing all measurement results that you have in a digital calibration certificate and then print it out to you on the screen, or providing it via an interface to another platform in your process. One example where we can have that beyond calibration certificates and certificates of conformity is if we would take the existing BIPM vocabulary metrology, the VIM, and further develop that into an XML or a similar structure where you can have a searchable structural hierarchy of terms, higher terms, relations between terms, and so on. Still, the information contained in the definitions in the Vim, the information contained in the individual measurement results elements is not machine readable. This would require level 3, meaning that the actual content can be discovered by a software, can be understood by a software, meaning the relation between different interfaces, between different sources can be understood by a software. Is the word force or the representation of the unit of measurement in one document related to that in another document or in the database that I have here? When I want to integrate the information from a digital calibration certificate into my existing internal database of measuring instruments, I need to have information about such relations. Otherwise, it's still manual work to adjust units of measurement, to adjust values, to adjust taxonomies, vocabularies, and so on. We have level 3. We can do this automatically based on further detailed XML tags specifying the different elements. Persistent identifiers, for instance, an identifier for a certain unit of measurement that we can refer to, that we know when it's in one document using the same PID as another document, or in the certificate the same as in our database, then we can be sure that it's the same unit of measurement and it's related. Or we can use linked data, which is a structural semantical way of describing the meaning of vocabulary and semantics. It means that we have to become much more granular in the way we specify the documents. Here's one example of how that may look like. You may have in a digital calibration certificate, you may have a measurement result that in detail looks like this. It has a label. You're saying it's a force value. You have the actual value, and they have the unit of measurement written in a machine interpretable way. There are many different ways on how to structure this. This is one example. This can be implemented quite easily in existing documents, but of course we have to have interoperability, so we have to at least find a way to how to harmonize and interpret these beyond different domains and use cases. Level 4 now extends this even further by also having the context of, for instance, the measurement of force available in a machine readable way, so that you can extract the information and can make use of the information automatically. So you have the software automatically working on the data without a manual workload, like the integration of the information from a calibration certificate into your internal database, or the interpretation of a standard and the information there to automatically adjust the calibration infrastructure or the calibration setup in your lab so that you can perform a calibration based on that standard, or at least checking whether your setup in the calibration is in accordance with the standard. However, it means we have to replace the now often implicit definitions and interpretations in our standards, in our guidelines, by some explicit semantic relations, because we don't want the machines to interpret widely what to do with the information. We want to be sure that when we have automation, that it works as expected. It starts, and we are working on that internationally, on the digital representation of units of measurement. It also means that we have to make the documents like the SI brochure, the Vim machine readable. First of all, because it is a kind of way for us to learn how to formulate things. It can then again be kind of a template for other areas, for guidelines and calibration, for standards in metrology and so on, that can use the way that we use in the machine readable SI brochure and Vim, and take that up to in other areas to again have interoperability. It also means that we have to talk about interoperable terminologies and vocabularies. The Vim is a starting point. We have the basic vocabulary metrology there with human interpretable interpretable definitions. It's only a glossary. When we have a high level of automation, and according to this graphic here, we need to go beyond the glossary. We may need, depending on how much automation we want to have, we may need to go up to ontologies. So explicit semantic representation of definitions, relations, and interconnections between terminologies and vocabularies. Right now, in the Vim, we have a glossary. We have a text that is written by humans and can be understood by humans, but a machine can make no use of this information right now. One example where this is of use, again, here with the example of a calibration certificate, is that we can then specify using, for instance, a linked taxonomy, what is this measurement about? Here it's a measurement of the radius of the length of radius. So it's clear the context can be interpreted by a software in the sense that it can relate this information to the information from another source, and in this way have an automated integration and use of the information from the certificate. And again, this is necessary because we are not doing this for our own. The certificates we provide in metrology are used in accreditation, are used in calibrations further down the calibration hierarchy. They're even used in conformity assessment and market surveillance. And of course, finally, they're used by the users to have their internal quality management systems and use of the information from the certificates. To take a step back from all these semantics, ontologies, and technical details, let's sum up why we do this. We do this because there is a digital transformation in society and economy. We have to address these developments. We have to address that we will see more and more large-scale networks of sensors with a flexible topology, meaning that sensors being added, sensors having failures, sensors being even mobile and being maybe placed on a car or on other vehicles or a drone. People use dashboards to assess the situation and the data. Dashboards compressing the information, again, meaning that not individual measurement is of that importance anymore. And we will see more and more data-driven decisions and automation based on individual measurements, but more and more also on networks of sensors. It also means that algorithms and software will become as important as the actual measurement. Also meaning that we will see more and more sensors integrated with digital technologies, with software and algorithms trying to compensate for unwanted effects or combining elements of different measurements to derive a certain measurement result. And it means for us that we will have more and more possibilities and opportunities for our own digital transformation, so automated processes in our laboratories and institutes based on such technologies. We will be requested to have digital interfaces between our systems and that of our customers, like providing the digital certificate not via email, but directly via a suitable cloud interface, for instance. We will have to build up competence in data science and artificial intelligence applications because, to be honest, this will be the future. These kind of systems will be integrated also in metrology systems. And we'll see more and more the interplay between cloud infrastructures and on-premise solutions, meaning that not everything will be in the cloud, but we will have localized solutions of measurement, but also of provision of services and data. Thank you very much, and I hope you have some questions.
Thank you very much, Dr. Antoine. That very interesting and very comprehensive presentation on this very topical issue. Now, this is open for discussion. Yes.
Sasha, this is Ashish from MPL. It's a very elaborate 20, 30-year plan which you have presented, and as an NMI, we need to have a start somewhere. So we talked about the sensor 4, and we talked about artificial intelligence, machine learning. So as a NMI, we all are metrologists. We are working in different areas of metrology, and this is something very, very new to most of us. And it requires a different skill set altogether. It seems to be a area in which we need to now venture into, and probably as a meteorologist, we need to learn, we need to do new things, and not only that, we need to also probably rely on a lot of new hardware, new software, algorithms. So it's also networking which we need to learn, the communication systems which we need to learn. So do you have a phase-wise plan of implementation in a NMI, where we should start with, what kind of skill sets, what kind of people we should hire, what kind of training a meteorologist should have, so that we can undertake this work in phases, because, and probably down the line we need to upgrade our hardware, the networks, the data centers. Uh, Probably as an NMI, we are not really geared towards this kind of plan which you are presenting today. And it's a very, very long-term plan. I know that. And you have talked about machine executability standards, which are kind of a fantasy to us right now. It seems to be somewhere we need to take a start. So we need to have a clear picture from PTP as a lead, that how an NMI should start at the first phase. I
Mm.
hope my question is clear.
Yeah, question is very clear, and it's a question that is very that I'm asked very often. And if I had a good answer to that, I think I could become rich. uh, um, I can only tell you from our experience and learning when we started going in this direction, and that is that we realized it's good to approach the customers that we have, the customers there for which we know are well advanced in digital transformation, that are using a lot of digital technologies already, and ask them, what do you need from us right now? What is the way you want us to provide the services? And then use this input um, as the way to identify what is needed internally. So this process, the internal digitalization, this is something we have started working on about 2 years ago. It helps us to identify uh, where we have homework to do regarding our own internal systems. But, and this is even more important, it helps us to identify the digital pioneers we have. And I think in all metrology institutes, you have people like that. People you have a personal interest and experience and competence in writing software, maybe using this to have certain automation in the calibration or in other processes in their lab, and who are very, very interested uh, and even happy to support the institute in pushing it forward in digital transformation. So the homework is done, and the task is done to enable these pioneers to to spread their knowledge, to um, make use of their competences for the better of the whole institute. Of course, um, it's a long-term um, project. It's something that we cannot solve in 1 or 2 years. As you said, it's a question of decades.
A second question I have is regarding the Martin did say in the morning that the BIPM already is implementing this kind of thing in the time department for long time while he's generating the UTC and TAI. So any comparisons which we can make from the time department to the implementation of digital transformation because all the NMIs are having some kind of time lapse and they are already having some kind of network dependency and some kind of traceability from BIPM. So is that it can be a starting point for an NMI? Any comments on that?
It can be, of course. I mean, it's always good to start with something where others, and in particular BIPM, providing services in a digital way. Um, it's kind of a low-hanging fruit, I'd say. Just recently, there was a publication on a digital transformation for a mise en pratique in the area of lengths, also published together with the BIPM, Martin Milton. So there are early developments of that. I think what is important, though, is to make sure that these kind of pilots are talking to each other, have an exchange of experience and information, and also try to agree on a common approach, a joint approach on the use of digital technologies, and also on the representation of units of measurement and data models to ensure interoperability. If we had um, a lack of interoperability already at this level, I think it will become very difficult, if not impossible, to have interoperability in the broader sense of the word.
Thank you. Thanks a lot. This is now very clear that we have to live with artificial intelligence, machine language, not merely in a small domain, but all over, wherever possible. And that is where perhaps this front of metrology is moving to. And I'm very happy to see what PTB is doing. PTB was at front when it came to hardcore measurements in opening new disciplines. I also was associated with some of them some times ago. So it's a very nice and very exciting presentation you gave, and also makes us think about what is in future for all of us. Thank you very much for a wonderful presentation.
Thank you very much.
Our next presentation is by Emal Desai. Is he there? Acha. Dr. Desai, yes.
टाइम दिखता है हाँ ठीक है ये दीजिए नहीं जैसे हम इसे प्रेजेंटर में आप वॉकिंग करके भी बोल सकते हैं इसका दिखाने से आप बताओ ये सब पॉइंट कर रहे हैं ये स्लाइड इससे आप कहीं से मूव कर सकते हैं यहाँ ये फॉरवर्ड है So good afternoon to everybody and namaskar. My name is Hemal and I represent a company called Anderson Hauser. Anderson Hauser, some of you might have heard about the company, but I'd just like to put on a slide to just introduce my company. But before I do that, my presentation will basically talk about more of a user's perspective in terms of what is reliability, field reliability in measurements in process plants. So I've worked almost more than 30 years in the process industry, process measurement and control part. And my primary job is to basically know what my customers' pains are. So I hope in the next couple of slides, I try to bring to you some of the things which a user thinks about in his mind when he talks about measurement. Okay, sorry, just use, it's not changing. Changing. Yeah, that's it. So we are part of a Swiss company, and as you know, Swiss are very. You hear about Swiss Bank, you hear about Swiss chocolates, you hear about Swiss watches. But many people are also aware that Switzerland is also a land where a lot of precision instruments are being made. And Andreessen has been in the process industry for the last 70 years, making very high precision process instruments and technologies. So I represent the company. We have been in the industry, almost all the process industries, including food and beverage, power, life sciences, biotech, chemical, oil and gas, any process industries you go, you will find our equipments being used for the last 70 years. In India also, we have been present for the last 40 years now. So when you go to a process industry and you talk about reliability, reliability means different things to different type of people in process industry. So some people think of reliability as how well I am able to control my process. So if you ask a process engineer or a person who's basically looking after the process or is looking after quality of the product, he is basically worried about how well I'm able to control my process. There are people who define reliability of, do I reduce my risk? How much risk do I have in my plant? There are some people in the industry who want to really avoid, mainly the maintenance engineers want to avoid an unscheduled shutdown. So they're worried about how much percentage of the time in a year is my process available to me for production. And then there are engineers like, utility engineers who would basically worry about how do I reduce my energy consumption, utility consumption, how do I look at cost of producing the product. So these are different definitions, different people look at reliability in different ways. So what we are going to focus in this presentation is basically from the quality perspective and from cost perspective, and we'll also look at it from availability and safety perspective. So we'll try to combine all of this from a process instrumentation point of view, and I'm going to present you a couple of slides from that perspective. So the reliability journey in the process control starts from measurement. Measurement is the first thing because it's very popularly said that whatever you can measure, that only you can control. So if you cannot measure something, you cannot control something. And if you cannot control something, you cannot improve on it. So these are all related, and the first starting point of the reliability journey is measurement. That's where we come in, or that's where I come from. And when you talk about measurement, the most common dilemma today in a process plant is that you have hundreds of measurements being done in a process plant. What is the integrity of that measurement? Okay, so I am seeing some measurements on my control system screen. What is the integrity of my measurement? What is the confidence level I have in that measurement? And how do I ensure this confidence level is there all the time? And how do I ensure that my measurements are accurate in real time? So this is the most common dilemma you will find in any process plant, especially some of the things, some of the plants like oil and gas or food and beverage, life science, this is very, very critical because your entire quality of the product depends on how accurately you can monitor the process values. So just to give you an example, that you go to an oil and gas plant, the expectation of a process control engineer would be that how can I reduce the variability in my process loops? Okay, this is the key expectation of any process control engineer in any process industry. How do I reduce the variability in my loop? Why? Because if you see any plant, okay, or any production facility, it consists of many these kind of loops. And if you are able to reduce variability in all these loops to a certain extent, the end product which you get out of this plant will be on spec, okay? Or your quality of the product is A1. You want X quality of the product, this is what you will get if you are able to reduce the variability across all the loops. And what we are essentially saying here is that if you can reduce variability, you have very tight control. When you have tight control, you have quality on spec. When you have quality on spec, my cost of production is reduced. My utility consumption is reduced. My energy consumption is reduced. So I have the most efficient way of producing the product at very high quality. That's how a process engineer looks at it. And there are many variables which actually can disturb this or can affect this. Okay. So for example, faults, if any. In all the control elements or measurement elements, if there's any fault, then you are in for a surprise. Or the accuracy of measurement is also a variable here. Of course, there are many other variables, process variables included, but I've just tried to pinpoint some of the variables which we'll be concerned with. Stability of measurement over time. How stable is my measurement? My accuracy may be A1, but if the measurement is not stable over a period of time in a process plant, then I have a problem. And process effects, which I already talked about. So there are some variables which really can disturb this process variability in a process plant. So one of the most traditional way of ensuring that we are doing a very good job in a process plant is to basically do a metrological calibration of the equipment, both measurement as well as the control elements over periodic, period of time. So typically when a plant is being started, usually you get equipments from the manufacturer. And before the manufacturer ships you the equipment, it is usually calibrated as a part of the manufacturing process. And once the equipment is received at the site and put into operation, again, most of the time the calibration is checked, and then you actually have a preventive maintenance strategy by which, let's say, every once in a year to ensure that the calibration is still on spec, or if you have to recalibrate the device. So you establish a period of time. Sometimes it's the preventive maintenance strategy. Every once in a year, I would calibrate, let's say, a flow meter. Okay? So that's usually the case. But from an end user's perspective, okay, this is an issue. There's an issue that you have to remove the equipment from the process for calibration. And some of the processes are very critical. For example, you have custody transfer process, or you have process which is maintaining. Let's say you are dosing something or you are mixing something. Then it's very difficult to remove an equipment from the process because you have to disturb the process. You have to stop the process. You have to remove the equipment. Sometimes you have to send the equipment from one end of the country to the other end of the country. And this takes a couple of days. So you have no measurement during that period of time. And again, when you receive the equipment back, you have to again put it back in line by stopping the process. So this is from user's perspective, something which he wants to avoid. And then there is documentation. You have to maintain documentation. You have to maintain traceability of the calibrating equipment, sometimes at the user's end or sometimes at the lab. So all these parameters play a role in how do you maintain the calibration of the device. So what is the easiest way out? Don't calibrate. So most of the users, even though they have a strategy in a document, a preventive maintenance strategy in a document, they don't calibrate. This is actually what happens in a process plant. So Anderson Hauser realized this because we have been working with so many end users in a process plant, and we introduced a digital technology which is known as heartbeat technology. Why we called it heartbeat was we say that this technique is like pulse of the measurement. Okay, so if I just take an analogy, if I'm not well and I go to a doctor, the first thing he basically sees is my pulse. So this is as good as a pulse of the measuring equipment which we produce and basically sell to customers. So why? What would this do? Basically enhance the reliability and confidence level of measurement. We are trying to give something to the client which can enhance his confidence in the integrity of measurement. Now, just a couple of slides on how this technique works or what this technology does. Just to give you a brief, sort of overview. This is there inside the device. So each of the device produced by Hauser has this heartbeat technology. It has basically three layers. You can see the three layers at the bottom. The first layer is the diagnostic layer. The second layer is the verification layer. And the third layer is the condition monitoring layer. So there are the three layers within the device. And just to give you a brief overview of what each of these layers do, uh, whatever I'm actually trying to show you, I really, identify a lot of things with the presentation from PTB just before me. Okay, so I'm happy that I am doing this presentation after a couple of presentations today morning, where you will be able to connect a lot of things which I'm saying to those presentations. So the diagnostic layer basically is concerned itself with, continuous monitoring of each and every field device. Okay, 24/7. So, each of this device today with the digitalization, what is possible are almost like you don't have a device, it is actually a computer in the field. So when somebody talked about nodes, yes, this is a device, this is a computer in the field, it acting as a node. Today you have IP-based sensors. IP-based sensors are what we see the trend in the process industry is in the old days, you had a lot of equipments which were connected by wires to each other. Today, we are seeing a trend with machine to machine or industry 4.0 where there are a lot of equipments, but they are connected not by wires, but by probably web. Okay. So this is a trend which is going on. And all this AI, MI, what we saw since morning, they are all tools being used in this entire ecosystem. So this is the trend. And when you say, when you talk about heartbeat, coming back to heartbeat diagnostics, there are a lot of these computers in the field, which we call as instruments, and they generate a lot of data. Now it's very difficult to understand this vast amount of data. So how do we collect that data, learn from that data, and present it in a way which is usable to the user? So in one of the presentations in the morning, we talked about telling the user whether the calibration is pass or fail. This is exactly what we are trying to do here. Okay. We are trying to collate this data. We are trying to study this data. We are trying to tell the user whether your equipment is okay or not okay. Okay. So this is the first layer. And what is most important is what you can see there is it has a diagnostic coverage of up to 97%. That is 97% of abnormalities in any device can be detected by this layer. Okay, which covers almost all. I'd just like to give you one example. I have an Apple Watch here. I'm not I'm not marketing anything, but I have an Apple Watch here. And this Apple Watch is continuously monitoring a lot of parameters from my body. And if it finds, let's say just an example, that if my heart rate is gone beyond the normal heart rate of a human being, let's say if I'm not exercising, I'm just sitting and walking, my heart rate should be between 60 and 100. If it goes below 60 or above 100, gives me an alert. So this is something very similar happening here. But here we are not talking about a single parameter. We're talking about hundreds of parameters being monitored and being collected and being shown. So this is the first layer. The second layer is known as verification. Now we all know that calibration is basically a metrological, assessment of a device. We are not trying to confuse with calibration. We are talking about verification, which is a comprehensive functional assessment on demand. On demand, when I say is just with a push of a button for any device, you can actually do a functional assessment. Okay, whether functionally device is still you can have confidence in the measurement or not. And when you do a functional assessment or when you do a verification, actually what happens within a device is that there are some internal factory references which have been built in the electronics, which are being compared to the current integrity of measurement. So current integrity not only of the measurement but also of the mechanical elements in the sensor, also of the electrical elements in the sensor and also the outputs. So all these are compared to some factory references. How are these factory references built into when the equipment, each equipment is being built? These references are created by calibrating those references with some traceable references. So that's how this is done. And when a verification is run, okay, on a process device, it takes care of both random failures as well as systematic faults. Okay, so both random failures as well as systematic faults are taken care of when you run a verification. It generates a report, which is known as a verification report within the device. Now, this is very, very unusual. You usually generate a calibration report outside, but we are talking about a verification report inside the device, which can be extracted and which can be printed or which can be stored. Okay. And this entire concept of verification, which we have developed almost since last 10 years now, is attested by third parties to comply with the ISO 9000, chapter 7.6, control of monitoring of measuring equipments. So this is one of the other layers which we bring in into the reliability discussion. And this verification can be done from anywhere. We talked about digitalization. We talked about digital transformation. So this verification can be done at the equipment level, can be done from the control room, can be done maybe using a tablet, can be done using a phone if the process allows, and can be also done via cloud from anywhere. Okay, so this is the level of sort of reliability concept which industry is actually using right now. So the verification brings in a lot of things. As we saw, it is very fast because when the verification is happening, your process is not disturbed. The process measurement is still on. Okay, it is safe because you don't really have to remove the equipment or send it somewhere. Confidence level is still big. You can have confidence level that I can elongate my calibration interval. It is documented, self-documented. Your document is available anytime, anywhere. It is traceable to a certain extent, and it is in situ. That means we don't really have to remove the equipment from the process to do this verification. So from the traditional perspective, when I had a preventive strategy that I do a calibration every once a year, okay, I can slightly tweak this strategy with the concept of verification, saying that, okay, every once a year I still do calibration, but every 6 months after the calibration, I do a verification test. Okay. And I can study the results, whether I am still able to get a good response from the integrity of the measurement or the sensor. And if I'm able to do that, can I extend this calibration interval? So let's say every once a year, can I move to every once in 2 years? So this will be a big help to clients which don't calibrate at all. And the last part is called condition monitoring. The last layer is known as condition monitoring. Any process device, once you put in operation, okay, there is always some amount of slow degradation happening. For example, it is possible that some corrosion may be happening within the device, which is going to affect the integrity of measurement. Or there may be some deposition happening within the device over a period of time, which affects its integrity. Or there may be, abrasion which is happening if you have slurries or if you have chemically active processes. So can we detect that? Yes, as I told you, this data can be accumulated and trained over a period of time to basically give you an information of how the integrity of the entire device or the integrity of the process measurement is getting affected. And beyond a certain point of time, it can give you an alert, yes, that now you need to really look into in detail to look at the reliability of measurement. Okay, so this is a new concept. When I say new, it's almost 10 years old. There are hundreds of plants in India which have been using this, mainly because they just want to have a better control on their measurement, more confidence on their measurement. And that's all I want to basically bring to you. Thank you very much. Uh, just to give you another slide, which is more product specific, is that this is today being available, this kind of technique is available in all different types of measurements. Okay, whether it's you're trying to measure process variable like flow, you're measuring process variable like level, temperature, pressure, liquid analyzer parameters, liquid analysis parameters, many different kind of measurements equipment has this concept now available in the market. So that's it. Thank you for your attention. If you have any questions, please, you can ask me now. I am also available. We also have a stall where you can basically see some of our digital, what we have basically shown there is the IIoT ecosystem where these equipments are integrated. So if you just want to have an experience on the IoT ecosystem, please have a look at the stall. Thank you.
Thank you. Thank you very much for your very clear presentation. Since there is no question, we can stop here.
Yeah, thank you so much.
Thank you. The last presentation of this section is by Mr. Harish Bajaj, Mitutoyo.
This one is also
अच्छा अच्छा आप ऐसे नीचे लिखो ना पकड़े होते हैं अच्छा ये नहीं कोई बात
Okay, good afternoon. Good afternoon. I see gentlemen mainly, ladies and gentlemen. We are Metrology, South Asia Private Limited. We are a Japanese company focusing on dimensional metrology. So I'd like to talk, a little bit about the introduction to our company, our facilities, the partnership that we're doing with the academia institutes in India, because we would like to highlight this and basically maybe give some takeaways in terms of what we can do and what we should do for enhancing the growth of the collaboration between academia and industry. Wanted to touch about digital transformation in metrology. I think this is something that is a topic for the day, for the hour, and what available options are there in dimensional metrology. Also, of course, taking on from digital transformation, which is the most basic side, to automation, automatic programming, and so on and so forth. So I'll cite some examples and go through that. So Metrology is a global multinational company. Our philosophy is to contribute to the principle is to contribute to the well-being of society through precision measurement technologies. And our quality first motto, which was founded in 1934, still remains today. Today we've got 120 locations plus, more than 44 countries right now, expanding even today, 16 plants. And we focus on quality by maintaining our manufacturing in Japan even today. I know there are a lot of questions regarding why not India, but there's a specific reason to that I won't get into all right now. But we do have collaboration across the globe between our subsidiaries, and of course we do have collaborations between the R&D departments, be it in the US, be it in Europe, and be it in Japan. And of course, there's a lot of feedback that goes back to our principles to say what does the Indian market need, right? Every market is different, and what we look at in India is also kind of a very interesting challenge today in terms of it's a culmination of what we see between what the developed markets are needing, but also in terms of shaping it with the Indian mindset in terms of what the requirements are. So in India, we've got 10 locations, 5 technical centers, over 120 staff, about 80% engineers. Our history in India began back in the 1960s. We are now, as I said, 10 offices. We just established our Bangalore Technical Center in 2021. Kind of made that in the midst of COVID as well. And we support the entire industry with the various support services that we have: calibration, contracting, measurement technologies, gauging technologies, application support, software support, of course, repair and service and calibration, and so on and so forth. Our technical centers are equipped with the latest products and softwares, part programming, complicated programs. We look at, be it a most basic, measurement, bottle cap measurements, electronic, aerospace measurements, so on and so forth. We can provide these solutions to our customers at the technical centers that we have. Now, our focus also, is in line with our Honorable Prime Minister's goal of scaling India. And we have a motto that we produce the able person before creating product. We run our own institute. We can only reach so many. So we partner up with various institutes to be able to skill the workers and the youth of India, because that's the need of the hour, frankly. I think equipment, technologies are very much here. Our colleagues in the industry, whether whoever you see today and outside the market, they're all global companies here. So the opportunity of getting hold of technology is not so difficult, but getting hold of skilled people for the manufacturing growth that is required at scale, that's the challenge we have today. Stocking. So I want to say, what we do, and we hope to encourage others as well. We work with small, big colleges supporting the students to use the measuring equipment that they need to develop products, to participate and compete in global forums, be it with IIT Delhi, earlier on with DITE, and so on and so forth. Even with Amity University, we've done. We signed an MOU with the National Council of Aeronautic Innovation and Research, housed at IIT Bombay. So we work with them to be able to provide solutions for aerospace measurements as well. We do a quick video. So we talk about digitization. Not sure if this would work, but we talk about digitization and automation. So now institutes in India also are setting up labs at the highest levels. So they say, hey, listen, we want to be able to help us to be able to set up a lab which takes into account not just measurement, but automation and data analysis, data collection, and going into that next level of being able to evaluate your data in a very, very robust, but yet efficient and I would say direct manner, right? So this is, unfortunately, the video is not showing up, but it's an automation technique between a CMM, coordinate measuring machine, a vision measuring machine, and a robot. Over here, you've got your screens that are focusing on the measurement data that they've captured, and also the analysis of that data in real-time basis. So somebody sitting in a particular part of the factory who doesn't have access to the shop floor can be able to take a look at the data coming in real time. So we do, of course, collaborations, won't get into too much. Just recently, we partnered up with the government of Orissa to be able to skill the youth of India for dimensional metrology. by creating a metrology center at Government IT at Cuttack, and also, of course, lending our technology, lending our knowledge, our expertise to work with them closely together to be able to kind of help them to be able to reach out to a lot more students than we can. Same thing with the MSME, NSIC, and with the government of Uttarakhand. So we have the widest range of dimensional metrology product, over 6,000 products and integrated computer-based metrology systems. They can be interconnected to form closed-loop measurement networks, which what we're talking about. I think handheld tools, folks would know about Metrology. But let's just talk a little bit about IoT in the measurement field, right? Today, increasing measurement efficiency by linking the design and measurement, everybody wants efficient, streamlined services. So this comes in form of both hardware and software. It's not just one, right? And then linking of that hardware and software as well. So one is, the data capture. We'll get into that. One is the data analysis, and this is basically where you take it to the next level of artificial intelligence, where today you have programmers writing code to generate a particular part program to measure their component. Tomorrow, by a click of a button, by entering basic data that one would have in hand, such as the PMI data, such as the GD&T tolerances, and so on and so forth, you can generate a program that is most efficient, which is the best program that one could write, the optimized program one could write, and you're saving about 99%, 95% of time. Something that takes 2 days can be cut short to an hour. That's what IoT and digitization is in the metrology world today. So, we've got, various aspects of IoT and smart factory in the measurement world, whether you look at, data collection, whether you look at data analysis, monitoring, whether you look at collaborations with robots and combining the robot and the measurement techniques on the shop floor, whether you're looking at automatic part programming, just one-click programming, and feedback in the machine tools. So, now more and more, customers are saying, hey, listen, we want the entire process automated. And from that perspective, we want the measurement data to go back to our machining center and then basically tell us whether we're doing something right or wrong, or have a particular outcome of that particular machine based on the data that they collect in real time. So this is one software. You see, like everybody is familiar that they would use a micrometer or caliper. Earlier technique is to be able to read it properly, to be able to write it down, and then enter it into a computer to make sure that the data is captured. Today, that's not required. That's not required at all. You've got to just basically click a button. You take out the errors that will be occurring with an operator who may not be as skilled to be able to read, to be able to write down correctly every day on an ongoing basis. Maybe he's making a mistake, which is just a clerical mistake. All that is eliminated. And you've got a click of a button, the data is going directly into the system without any issues whatsoever. So, we talk about integrating factories, and what is that exactly, right? So the old school is, and even today, I would say too old school, but the system is inspection. You've got your quality inspection rooms where parts come in for measurements, and whether that's on a sampling basis, whether it's on a 100% basis, depending on the company, depending on the product. That's normally what people are deploying to ensure that the quality of products that they produce are as per tolerances and as per defined. But today, what's happening is that's not enough. They say that, hey, listen, we want all this data that's coming in the production line also to flow in to our quality management systems, and then be able to analyze it, be able to act upon it, be able to take real-time decisions. You've got, for example, in the industry, when folks are measuring components, you measure something on a sampling basis, they measure something with a lab. Your machining centers are not going to stop. Your machining is ongoing. So they're still producing parts. And what's going to happen is when you do find out that you've got an error and you got to need to change the tools and so on and so forth, you've already produced n number of parts. That's wastage. That's a real cost to manufacturers. So they say, hey, listen, we can't, in today's day and age where competition is stiff, where efficiency is so required, productivity is so required, we want this data from the production line coming into us real time. So this is what a software would take care of. You'll take the inspection room data, be it a CMM or roundness test, a vision test, and so on and so forth. You take your production line data with your measurement gauges, and you bring it into a particular software with SPC, and you're analyzing the data in real time. Then further from here, you can take that into your quality management system, then you link it with a particular PLI system, right? So the advantage is it improves work efficiency, integrated management of data, and easily deployed, right? So, you talk about smart machines, you talk about Industry 4.0. Let's go back to history in terms of where we started. Back in the 70s, when 70s and 80s, well, after this, computers became mainstream, machine automation started, right? CNC machines and so on and so forth. 2000s, we got the self-service technologies that got deployed. Today, where are we? One would say, hey, listen, are we in cognitive machines? You're talking about neural networks, you're talking about machine learning and deep learning and AI and so on and so forth, or are we talking about integrated with smart robots and stuff? We'd say it's a combination of the two. A combination of the two because both are yet readily available. However, not fully deployed yet with all the manufacturers to realize the full potential of what this new technology can offer manufacturers in the industry today, right? So this is just another example. Again, I'm not sure the video will work. But just to give you an idea, this is a CMM head, a coordinate measuring machine head. These are parts on a shop floor. They're coming in. It's housed as an automated system. The CMM would measure these components without a manual intervention. You'll have these parts being going go, no go, and then just move out to where they need to move out. You can see the space that it occupies is quite small because, of course, shop floors do not have that real estate to offer to house more and more equipment. So from that perspective, it kind of works for the manufacturers also to be able to install a small head to be able to measure the components of a particular size. This is something of integration with the robot again, robot and the CMM. You've got a conveyor over here. You would have been able to see the robot picking up the components, bringing it to the CMM, and then of course, after the measurement cycle is over, say, hey, listen, is this within tolerances or not? And you've got an automated process without any human intervention whatsoever. Everything is CNC controlled, everything is programmed, and you've got a fully automated measurement process in place. So these are just additional products that we would be able to provide to our customers to enhance efficiencies. When you look at what folks are looking at, is not just in the quality room, but they're now looking at these kind of measurement equipment for R&D purposes, reverse engineering, and so on and so forth. So these kind of probing systems helps with that particular process. Today, you talk about Apple, you talk about Samsung, you talk about semiconductors. Our government is also focusing a lot on increasing this kind of activity for setting up manufacturing units in India. And the biggest adoption right now is going from tactile measurement to non-contact measurement because the parts are small. Tactile cannot measure properly in terms of what you need to measure. So more and more non-contact measurement is being part of the play. So on that note, I'll end my presentation. And if there are any questions.
You made a very clear presentation. Thank you.
Thank you.
ठीक है
मोबाइल से नहीं मोबाइल नहीं हो गया पॉइंटर ये सब है कौन सा ये
Good afternoon, everyone. Before I start my presentation, thank you so much for NPL and Admit 2022, especially Shivagan sir and Jaiswal sir for giving us opportunity to speak here. So ICE Asia is a 30 years old company, and we have been representing various overseas company for sales and after sales service support. We are a ISO company, ISO 9001 2015 company. So as I mentioned, we are representing various overseas companies. So Amitech, Alpha Moisture, these are basically for process instrumentation. Then IROX, Protea for gas analyzers. Then ATG is for again biogas analyzers. Lumasys for IR temperature measurement, black bodies. And there are few equipments also like Tetron for material handling and all. So this may not be a specific product for metrology. We have few products for thermal metrology, basically for IR measurements. So this is ultra fast, high temperature black body, temperature having 3000 degrees C from 600 to 3000. Then we have a few test and measurement for vacuum applications, very low temperature application, black bodies, up to very high temperature black bodies. We have night vision testing facility. Then we have polymeters. Basically, all these products are for infrared calibration and measurements. Then we have few vacuum compatible black bodies, which we are already there in ISRO and few DRDO. Then we have collimators for calibrating infrared cameras or infrared detectors. Then we have specific software for integrating all these black bodies and IR devices. For so one software is useful means for integration of all the products. So then we have a specific IR test bench for detector development. So in this you have a different characteristic you can calibrate with the test bench. It has got black bodies, then collimator, then motion sensor. There are many bias voltage. Then there are many like you can measure like RMS noise, fixed pattern noise, then NDTD. These are the typical characteristic with the IR detector. So we have entire setup available, which is already installed in SSPL. Then we have few IR thermal cameras. Like these are cooled cameras having very high speed, up to 3000 frames per second. So these are also very useful for projectile monitoring or any like chemical war is there. So for that, hyperspectral cameras are useful. Then we have very long range cameras also for detecting spacecraft or which is coming from very long distance for defense activities and all. And then we have a few thermal cameras for NDT application, non-destructive testing application for active thermography application. So we will provide entire solution for this active thermography for NDT application. Then these are a few installations, like important installations for black body and other IR devices. NPL is one of our prestigious customer. And then we have installation of vacuum black body in ISRO. Then we have many installation, high temperature black body installation in DRDO. We have one in Fairlab and one is in IPR. So thank you so much. If you have any questions for IR related measurement, please let us know.
Take a comment or?
Yes, we have one installation in Fairlab. So
Okay,
Thank you so much.
for your presentation. I think with this session is over, or you have to? Acha, thank you very much, everybody, for their presentation and even the support teams for making it happen very nice.
Thanks to all the eminent speakers for sharing their views with us. I would now request the chairperson of the session, Dr. Krishan Lal, to felicitate Mr. Hemal Desai with a memento. Mr. Hemal Desai. I would request the chairperson, Dr. Krishan Lal, to felicitate Mr. Harshad Patil with a memento. Thank you, sir. Now I would request the chairperson to felicitate Mr. Harish Bajaj with a memento. Thank you, sir. Now I would request Dr. Sanjay Yadav, sir, to honor the chairperson and co-chair of with the token of remembrance. Thank you so much. Now I will invite all of you for lunch at Dr. A.R. Verma Grounds outside the auditorium. We will again gather for the next session after half an hour.